Hey everyone, Mr. Schachter back at you with graphing derivatives, this time taking a look at graphing a derivative given an original function, and vice versa, graphing the original function if you were given a graph of its derivative. Let's jump in. So I did a quick example on Desmos just to kind of use as a jumping off point for us. And in blue here we have this cubic polynomial, and in red we have its derivative. And let's go ahead and find some interesting observations. I'll summarize on the next slide too, so don't feel like you need to write them all down right now. Interesting observation number one is that right here on the blue function, we have a relative maximum, right? And that's evident on the red function right here as a 0, okay? And specifically here again, a relative minimum of the blue specifically corresponds to a 0 of the red one, right? You might ask, well, why is that? Well, remember that a derivative measures slope, right? So if the slope of the blue curve is positive, 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 positive slope, notice that the value of the derivative is positive. The sign of the derivative, the y value of the derivative is positive, okay? And then we go until we hit our relative max, and then right at the relative max, the derivative is 0. The derivative is 0, right? Horizontal tangent would occur there. Then what's going to happen is we're going to switch now to a decreasing derivative. The derivative is now going downwards. It's sloped negatively. And that's reflected by, I'm going to erase because it's getting a little busy, but that's reflected by a negative derivative, right? The derivative is now negative. Again, getting a little busy, so I'm going to erase the writing, but you kind of get the idea here. And let's look at the other one. So this right here represents a decreasing function, and this is when our derivative is negative. And then when we switch from decreasing right here to now increasing, now our slope is positive, and as a result, our derivative is now positive. Okay? So just remember that derivative means slope. So if a function is sloped negatively, the derivative has a negative function value. And if the function is sloped positively, the derivative has a positive function value, positive y value. Okay? So here are a couple of really big important points. Point number one, if the derivative changes from positive to negative at x equals a, the original function has a relative max at x equals a. And vice versa, if f prime changes from negative to positive at x equals b, the original function f has a relative minimum at x equals b. And also just remember that a negative derivative, so a negative f prime x means that you have a decreasing f of x. And a positive derivative means you have a increasing function. Okay, so these are like the big takeaways from this this particular section, so to speak. So let's go ahead and look at some examples. I'm going to give you guys a little sheet of examples, and I'd like you to see if you could match each graph to the graph of its derivative. Take a moment and give them a try yourself. All right, let's go over your solutions. Let's examine the first graph before we take a look at what it matches. So the pattern here is that your function from negative infinity to 0 is decreasing, right? Is decreasing. That should correspond directly to a negative derivative. So the derivative should be below the x-axis. Then we have a change from negative or decreasing to increasing. So that should be a 0 of the derivative, right? This should be when f prime x is 0. And then we have an increasing function from 0 to infinity. And from 0 to infinity, an increasing function means that the derivative should be above the x-axis. So that corresponds to graph C. So we've got graph C. Okay? The next one, we have a increasing function from negative infinity to 0. So this is a positive derivative, so increasing function. We then have a 0 here. It's a relative max specifically. So this should be when f prime x equals to 0. And then we have a decreasing function, decreasing. And if we find the graph that matches with that, It looks like it's going to be graph D. This is it. So this is it. So we got that relative max there. So this one's graph D. Okay? Whoops. Wrong letter. You go up there. There you go. So we've got our C and our D. Let's keep going. This one now, interestingly enough, so this one is a decreasing function followed by our change in decreasing to increasing, a relative minimum, followed by an increasing function. So this one should have a 0 somewhere around, what is that? Is that supposed to be 2? At x equals 2, we should have the derivative should be a 0. And then from negative infinity to negative 2, or negative infinity to positive 2, the derivative should be below the x-axis. So from negative infinity to 2, it should be below. This looks promising. And then from 2 to infinity, it's above. So there we go with A. This is us. A. Okay. Let's try this one. This one is same kind of idea. This one we're going to be at x equals 1 though. So we have a decreasing, a 0, and an increasing. So this time we should have a negative derivative, and then at x equals 1 we should have a 0, and then we should switch to positive derivative. So negative derivative, x equals 1, it looks like this is us. X equals 1, and then positive derivative, so choice B. Choice B. Last one, we have a negative 2. Negative 2 is the 0 here, so we are decreasing, we are 0, we are increasing. So this derivative graph should be at negative 1 or negative 2, the derivative should be 0. At negative 2, the derivative should be 0. That looks like it's choice E. And then we're changing from negative to positive at those values. So this one is choice E. So I think we got them all. Fabulous. Moving on. Here's a graph of an original function. Let's see if we could sketch one example of the derivative. Now, we may have answers that differ a bit, but they should have some of the same criteria. For example, criteria number 1. At this value right here, and it's a little tough to tell exactly where because I just sketched this real briefly. This is where our original function changes from increasing to decreasing. Increasing to decreasing, okay? So what that means on the derivative is the derivative should cross the x-axis right there, and our derivative to the left of that point should be positive, and to the right of that point should be negative. I'll wait a moment to sketch it, okay? But that's kind of what we've got so far. I also know that right about here, I'm also going to have a 0 on my derivative. Okay, a 0 on my derivative. And I'm going to actually switch the color so we're not confusing ourselves. A 0 on the derivative. And the derivative is going to be decreasing, decreasing, decreasing. My original is decreasing. So my derivative is going to be negative everywhere there. And then I'm going to be increasing, increasing, increasing. So my derivative is going to be positive. I think I'm ready to sketch. So I'm going to make sure that to the left of this value right here, this one to the left of that one, I'm going to be positive. So we're going to go like something like this. And then I'm going to have to now go into the negative region all the way until I get to this point, negative into this point. And so again, I'm kind of estimating where I'm going to drop this function. So I'm just going to go like that, and then we're going to go back up. So I'm negative there, and then I switch to increasing, increasing, increasing. Original means positive, positive, positive derivative. So this is just one graph of f prime x, just kind of eyeballing what I think would be a good representation. But those x-intercepts are very important. All right? Okay, let's try a couple of problems here. Number 4, if this is true, then at x equals 3, what is g of x doing? Well, I haven't really taught you how to infer those, but we can just automatically assume one thing. This right here is the alternate definition of the derivative, right? Which means it's the slope. I'm telling you the slope is negative. So if the derivative is negative, if the slope is negative, then by definition, the original must be decreasing. 100% true, that's the answer. So we don't even have to worry about C, D, and E. I hadn't taught you any of that stuff, but it's still a good question. So you can answer that question with the knowledge that we just learned. All right, we're going to use this graph for the next problem. I did paste it down here So let's just look at the question. Okay, here we can fit the whole question right there. Here we go. This looks fun. So if this is the derivative, so down here in this little box, if this is the derivative, which of the following could be the original? All right, interesting. Well, the one thing I really like to examine are the x-intercepts of the derivative. And this right here is going to be also 1, but it doesn't actually change. The derivative, this one's really interesting because the derivative doesn't actually change from negative to positive or positive to negative. So at this point, x equals 1, we actually shouldn't really have a relative max or a relative min. I just think that the original graph is going to go horizontal for a quick second and then kind of keep on going because we don't change back to a negative slope. We just kind of keep on going. So let's go ahead and first use the easier criteria. At negative 2, the graph should actually have some kind of a relative extrema. Now, what is that relative extrema? Well, the derivative changes from negative function value to positive function value. So if the derivative changes from negative function value to positive function value, that means the original should have a relative minimum. So a negative to a positive converts to a relative minimum. So at negative 1, where do we have a relative minimum? So at negative 1, we have a relative minimum. Let's see. It looks like, is it at negative 2? Sorry, at negative 2. So it looks like A is okay, B is a flop, C is a flop, and E is okay, and D is okay. All right, so those ones are good. And then what else do I know? And then I know that my derivative is going to be positive everywhere after. Positive derivative, positive derivative, positive derivative, positive derivative. So I know this function should actually never decrease again after x equals negative 2. It should never decrease again. So A's out because it decreases right here. And that's not okay. That's not what my derivative is showing. And E is out because my function turns and starts to decrease again. So E is out. So my winner is choice D, and it's notable to add, I'm going to erase this because it looks a little busy. At this specific moment, we know that the graph goes horizontal for a minute, but still remains to increase, and that is exactly what is evident with this particular one right there. Okay? One more example, a few different parts to example 6. Let's go ahead and look. It says the original, or the graph above shows the derivative of a continuous function between 0 and 1. All right, so this graph that I'm looking at right here is the derivative. I'm going to write that up here so I don't forget. Okay? A, for what values of x is f increasing? Justify your answer. Well, this is the derivative. So f is increasing whenever the derivative is positive. So when f prime x is greater than 0. Okay, so let's find it. Well, it's positive here, and it's positive here. So I think the answer to A is going to be the interval from 0 to 2. So A, the interval from 0 to 2, joined with the interval from 3 to, what is that? It's supposed to be 5? I think that's supposed to be 5. I think this number right here is supposed to be a 5, not a 1. I think I said 1, apologies. 3 to 5. And the reasoning, the logic, the justification is that since f prime of x is greater than 0 on those intervals. Okay, so when f prime of x is greater than 0, I know I have an increasing original function. B, for what value of x does f have a relative minimum value? So relative minimum value of the original means the derivative needs to change from a negative to a positive. Okay? So I need to change, my derivative needs to change from a negative to a positive value. That looks like it happens right here at x equals 3 because I changed from a negative function value to a positive function value. So I'm going to go down to B, and I'm going to say at x equals 2, since, it's at 3, sorry, x equals 3, since f prime x changes from a negative to a positive value. Okay? All right. C. For what values of x does f have its relative maximum value? So now I'm just really looking for a positive to negative change, right? A relative max is when you go from a positive to a negative change. So looking at my graph, I think that's going to occur at x equals 2 because I'm going from a positive derivative down to a negative derivative. So I know I have some type of relative maximum at x equals 2. And you may think to yourself, Mr. Schachter, this looks really weird because it almost looks like a jump discontinuity. But this is the graph of the derivative, okay? So for all we know, the original function could be continuous at x equals 2. It just may not be differentiable there, which is something we don't explore until next section. Okay, but don't think of this as a jump discontinuity. This is just simply that the derivative is changing from positive to negative at x equals 2. Okay, so this is at x equals 2 since f prime x changes from, and I'm just going to abbreviate, positive to negative. Okay? D. If f of 1 is 1, use a, b, and c to graph this thing from 1 to 4. Okay, so if f of 1 is 1, I'm just going to erase this. I'm going to get a new color. If f of 1 is 1, and what did I say in part A? So in part A, I said from 0 to 2 and from 3 to 5, the original is increasing. I also said in part B that x equals 3 is a relative min. And I said in part C, x equals 2 is a relative max. So x equals 3 is a relative min. So x equals 3 is a relative min. I'm going to just draw like a happy face. And x equals 2 is a relative max. I'm going to draw like a sad face. And then I'm just going to go ahead and complete the graph. So I'm just going to go across, I'm going to go up there, and I'm going to go down there, and we're going to go back up, something like that. So we'll kind of draw it a little bit smoother now. Something along these lines, and we have to stop at 4. Stop at 4. Okay, so we have right here, we have our relative maximum value. Right down here at 3, we have our relative minimum value, and this reflects what the derivative is doing, right? Let's verify for a second. So from 1 to 2, the derivative is positive, which means the original should be increasing. That's true. From the left of 2 and the right of 2, we changed from a positive to a negative, which means you have a relative max. From 2 all the way until it looks like 4, from 2 until 4, we're going to be well, actually, let's break it up into 2 pieces. From 2 to 3, we're a negative derivative, which means we have a decreasing function. And then from 3 to 4, we're a positive derivative, which means we are an increasing function. So this is just one representation of what the graph might look like from 1 to 4. All right?